Hello everyone, welcome to the INS lecture series, that is the Information Network Security lecture series. This is lecture number 8. In this particular session we will study about AES, that is the Advanced Encryption Standard, the structure of AES, structure of each round of AES and the advantages associated with AES. Now what is AES? So Advanced Encryption Standard, it came after DES and it was selected by NIST because it was able to satisfy the following criteria. These were the criteria which were satisfied by AES. The first one was the security part. So with respect to security, it is seen that the size of the key is starting from a minimum of 128 bits. So there are 3 versions of AES, and out of the 3 versions, the minimum the version 1, we can say the size of the key is of 128 bits, and the other 2 versions they have more than 128 bits key. And we know that for security purposes 64 bit key is the minimum requirement and is almost double of that, so 128 bit key. Then with respect to cost, the cost of hardware and software for computational efficiency storage, so it is seen that it is cost effective. The hardware and software required are not much complex, and even the implementation, so it gives flexible algorithm and implementation on any platform. So we get a lot of flexibility with respect to the implementation with respect to the platform. Now this is the structure of AES, the block diagram of AES, we can say. So it processes a plain text of 128 bits, okay, and it gives cipher text of 128 bits, and the key, it can be either 128 bit, 192 bit or 256 bits. So there are 3 versions, okay. So it actually takes 2 inputs, the encryption and the plain text and the key, okay. So there are 2 inputs for the encryption process, okay. There are 2 inputs for the encryption process. One is the plain text, other is the key, and there are 2 inputs for the decryption process, the cipher text and the same key, okay. Now this is the structure of AES, okay. So as we can see here, in this particular diagram, just zoom the diagram if you want. So as we can see, this input is plain is the plain text of 128 bits. It goes through a pre-round transformation through a key of which is of 128 bits. Then there can be n number of rounds, okay. The data goes through n number of rounds. The output of first round becomes the input of second, the output of second becomes the input of the third one, and so on. For each round we have a key expansion, okay, system which generates 128 bit keys for each and every round, even for the pre-round. And here as we can see that there are 3 versions actually, okay. So in the first version, the key size is of 128 bits and there are 10 rounds, so this n would be 10 for that case. And there are another version has 12 rounds and the key size of 1 bits. The third version has 14 rounds and the key size is of 256, okay. So these are the size of the keys: 128, 192 and 256. But it must be noted that for every round, irrespective of whatever version we are using, the size of the sub keys, so these are the sub keys as you can see, K1, K2, K3 and of course K0, K1 to Kn, these keys are of 128 bits irrespective of what the size of the actual key is. So this is the actual key and these are the sub keys, okay. Now the structure of we'll study point wise. So the first point is A is a symmetric cipher. Symmetric means what? The same key is used for encryption and same key for decryption. And this AES, it comes under the category of non-feasible cipher. So it is a non-feasible cipher, okay. We do not divide the data into 2 halves, process one half and do the second half differently. Here the entire data is taken all together, okay. So this is a non-feasible cipher, and of course it is a block cipher because it operates on a block of 128 bits. Then this point, it says it encrypts and decrypts a block of 128 bits at a time, okay. If the data is less than 128, we have to do the padding, okay. And if it is more than 120, we have more number of blocks. Then the size of the key depends on the version used, as we saw. It can be either 128 bits, 192 or 256. Then the number of rounds are also, they also depend on the version. there can be 10 rounds, 12 rounds, or 14 rounds. These are the three versions, as we can see. Okay, so for version 1, as we can see, the key size is 128 bits and the number of rounds are 10. And for the second version, we have the size of the key is 192 and the number of rounds are 12. And for the version 3, 256 and number of rounds are 14. Okay, so the plain text, it undergoes an initial transformation before going to round 1. Okay, so it goes through a pre-transformation and the key is K0 is applied. Okay, and irrespective of the version, the size of the sub key is always of 128 bits. Okay, and the sub key generates n plus 1 keys. So if the number of rounds are 10, 11 keys are generated. If the number of rounds are 12, 13 keys are generated. If number of rounds are 14, 15 keys are generated. The extra keys applied to the pre-round transformation. Okay, now there is the structure of each round. Okay, in each round the data goes through various processes. Okay, so here, as we can see, something we call it as a state. Okay, this state is the arrangement of the bits, 128 bits. So we can assume that this is arranged in a form of a matrix. Okay, with 4 rows and 4 columns. Okay, so this is one state. Okay, so here the data is of 8 bit, then again 8 bit, then again 8 bit, then again 8 bit. So this is actually 32 bits, 32 bits, 32 bits, and 32. So this makes up a 128 bits entire data. Okay, so it is arranged in the form of a state. So first is the first thing which is applied is the sub byte transformation, which is called substitute byte transformation. So after doing this sub byte, this state changes and we get a new state. Then it goes to another operation that is called a shift rows operation. So after shift rows, again the state changes. Okay, then it goes to the mix column transformation, again the state changes. Okay, and we have this. Okay, and finally we have the round key application. So after round key application, we again have this state. So in each and every round, all these functions are applied. Okay, so but in the there is a change in the last round. Suppose if we are using 10 round, okay, suppose we are using a 10 round version, then in the 10th round mix column is not there. Okay, so this operation is absent in the last round of each version. Okay, this operation will be there in all the rounds except the last round of each version. Okay, now structure of each round, as I explained. So sub byte, in this what happens, each byte from the given state undergoes a substitution from a predefined table. We'll see this. So this transformation is reversible. Then we have shift rows. So in this case, the bytes undergo left shift operation. Okay, so the operation is such that the first row has no shift, the second row has 1 shift, 1 left shift, third has 2 left shift, and fourth has 3 left shift. Then we have mix column. So mix column, each column of the state is multiplied by a constant 4x4 matrix. So we get another column matrix. We'll see this afterwards. Then we have add round key. So in this transformation, each column of the state is actually XORed with the corresponding column of the key matrix. Okay, it is coming in the further slides. Now see what happens in sub byte transformation. So this is just an example. We don't need to remember this. Just for explaining purpose, I've written here. So this is the state. Okay, then if we apply the sub byte, so for making this sub byte, we make substitutions. So we take the first byte. Okay, this is the first byte, 1 0. Now 1 0, to get the substitution for 1 0, we see this table. So in this table 1 0, so we have 1 here and 0 here. For that 1 0, we get the substitution as CA. So this CA is replaced here. Okay, so 1 0 is replaced by CA. Okay, the second byte is 1A. Okay, so for 1A we do the same thing. Okay, so here we have 1. Okay, and here we have a 1A. So for 1A we have A2. Okay, so we substitute this by A2. 1 is by A2. Same way all the substitutions are done. Okay, then next is shift rows. So suppose we get this is the output from the previous operation, that is sub byte. Now in the shift row operation, the first row, as you can see, it is same as the first row of the this transformation, so it is not changed. Okay, the same as what we get in the first row in the previous case. Now in this case, what we see, this there is a shift. Okay, what shift is that? This 21 is shifted here. Okay, and this all the bytes, they undergo one bit left shift operation. So this 1 8, it comes here, B8 comes here, 5D comes here, and 2 1 goes here. So this is what we get. In the third row, 2 bytes are transformed to the left. Okay, the bytes, actually all the bytes are transferred 2 places to the left. Okay, so 9 1 comes here, 4 6 comes here. Okay, and this is 4A comes here, and so this is after performing the left shift, and this undergoes 3 left shift operation. So 7 9, which was here, it comes here. Okay, 8 2, which is here, it comes here, and so on. Okay, so it undergoes this 3 shift left. Okay, so this is how it we get this. Okay, then the next operation is mixed columns. Now with respect to mixed column, what happens after this, what auto output we are getting from the above operation? So here we select the leftmost column, the first column, and this column is post multiplied with a constant matrix. This is the multiplication process, the matrix multiplication. Now this is a 4 by 4 matrix, and this is 4 by 1 matrix. So this multiplication is possible because the number of rows of number of columns of constant is equal to the number of rows of this. So the product will be 4 by 1. We get another column matrix. So we get another column matrix. So what happens in this case is, this column is replaced by this one. Then we take the second column, multiply with the same matrix. Okay, and we get another column. Okay, and similarly we get all the other columns. So we get this. Okay, after mixed column operation. Now this mixed column operation is there in all the rounds except the last round. Then finally we have the add round key. Now what happens in case of add round key? Whatever output we are getting from the mixed column, this one, left one, okay, this column of this is actually XORed with the round key. So this is the function where round key is applied. So this column is XORed with the first column of the state is XORed with the first column of the round key. So this is the XOR operation, this with this, and we get this. Okay, then second column of this with second column of this, third with this, fourth with this, and we get the output. So this is the output of the first round. This goes to the second, third, fourth, and so on until we get the final output. Okay, now let us see what are the advantages of AES. Now with as we see, the advantages is the key size. Okay, so security requirement demands that the key should be of at least 64 bits, but here we see the minimum is 128 bits, so it is quite large, and maximum is 256. And this avalanche effect is AES strongly satisfies this requirement, that if we change a single bit then a large number of bits change in the output. Then completeness effect, so whatever output we are getting at the ciphertext, even 1 bit, that 1 bit is the result of many number of bits in the plain text. So this requirement is also satisfied in case of AES. So that's all for this particular session. Thanks for watching.